So my name is Christopher Etienne. I am the Student Engagement Coordinator for the Prison Teaching Initiative here at Princeton University, which just means that I help students connect with the resources that they need to successfully complete their internships. So today, we're giving our students the opportunity to present research that they have been working on for the last 9 weeks. Presenters are hailing from 3 different internship opportunities, including the CFR internships, or the Coding Foundation of Research internships that is directed by Dr. Marian Alberti and Professor Jenny Green, our REU internships, or Research Experience for Undergrad, that is directed by Dr. Bridget Von Holt, and our ASAP internships, also known as Aspiring Scholars and Professionals, that is directed by Dr. Afia Ofori-Mensah. Today, I would like to reflect on the impressive feats of these students. Our interns enter these programs with no formal training or exposure to their research projects that they are assigned to. They receive a crash course in fields that people spend a lifetime researching, and they create thoughtful analysis and summaries of these topics, often expanding upon the research itself. Today's symposium isn't simply a nod to their academic prowess, it is an acknowledgement of their scholarly prowess and their academic fortitude. It is a proclamation for students who are bold enough to forge their determination into keys of curiosity that they use to open the doors of opportunity. It is our honor and our privilege to set a stage for these esteemed scholars. We are grateful to be mediators, and we are thankful to announce their accomplishments and boast about their abilities. But it would be a disservice to consider today's event just to be an acknowledgement of their talents. This is a declaration for diversity, an evocation for equity, and an inclination for inclusion. It's a demonstration that highlights the importance of building pathways and bridging divides. As I look upon our counselors, mentors, instructors, and directors, I sense the spirit of organizers who answered this call to action. As I gaze upon the audience, I see family members, and loved ones who are selfless enough to use their backs as bridges and their shoulders as rungs that these scholars currently stand on top of. We recognize your support and are grateful for your contribution. I ask that you once again put your hands together for our esteemed scholars. And with that, I would like to invite our fearless CFR leader, Dr. Marian Alberti.
Good morning. It is incredible to see everyone here. I am going to now invite all of the interns who participated in the 3 different programs, so the CFR interns, the ASAP interns, and the REU interns, to come stand and line up over here. We'll be doing lightning talks. So today, the interns will start by introducing you and inviting you into a longer conversation during the poster session. So everyone will have 2 minutes to share what they did this summer and pitch to you essentially why you should come and talk with them during our poster sessions. So they'll be going in alphabetical order, and they'll have 2 minutes. You'll come up here and stand at the podium, and at the end, we'll ask you to go and sit back down with your friends and family in the audience, and we'll move on to the next speaker. Applause is, of course, always welcome. And after the poster, or after this lightning talk session, we'll list on the screen here who's going to be presenting either at their poster. At the front, the ASAP students will be taking over this table to do a display presentation rather than a poster, and you'll have time to meander and talk and hear all about the incredible work they've done in a lot more detail. So, with that,
hello, my name is Annabelle DePasquale, and my data explores the amount of spiral galaxies in our universe versus the amount of spiral galaxies in a simulated universe generated by a computer. The purpose of this research was to see how similar the generated universe was compared to our own. It is important that the simulated universe is like our own because it's a resource used to replicate galactical events that we can't see in real time due to them lasting for longer than a human lifespan. For example, the collision of two galaxies or the life cycle of a star, which can take up to millions of years to complete. Simulated universes are the only way we could test theories of the universe because we don't get to see these events in real time. These replications allow us to develop a better understanding of our universe. So it's important that the simulated universes reflect our own as closely as possible. My graph shows the percentage of spiral galaxies in the universe versus the universe at change. The black line is our universe, and the pink line is simulated universe. As you can see, the amount of spiral galaxies in the simulated universe falls a little short of our own universe. My theory is that this difference is due to the data used to generate the universe being the Hubble Space Telescope data. This would cause issues because the quality of the images taken by this telescope was not as clear as the James Webb Space Telescope data, which is the data I use to represent our universe on this graph. The poor quality of the Hubble telescope images caused a lot of spiral galaxies to be misidentified as other types of galaxies. You can come by my poster to learn more about it. Thank you for everyone who came today and to all my instructors who I could not do this without. Thank you.
Good morning, everybody. My name is Richard Doherty. And today I want to share a surprising discovery that's changing how astronomers think about galaxies. For a long time, astronomers believed in a simple rule. Blue galaxies are spiral-shaped and full of new stars. Red galaxies are elliptical, smooth, and made of old stars. But with my analysis of simulated galaxies, combined with breakthrough new technology in astronomy, it shows a slightly different story. Using illustrious TNG simulations, I analyzed and plotted the colors and ages of stars in probable spiral galaxies. As you can see there. Some of the spiral galaxies in data follow the expected trend, young, blue, and star forming. But then over there is RS-14, or red spiral 14. It's old, it's red, and no longer forming new stars. Yet it is still spiral-shaped and it lies much further out in space. Why haven't astronomers seen galaxies like this before? Because older telescopes like Spitzer can only show them as blobs. But then came the James Webb Space Telescope. With its sharp vision, it covers a broader and more sensitive part of infrared light spectrum, including deep infrared, which is ideal for studying galaxies. Astronomers finally saw these galaxies clearly. One of the most exciting galaxies they found was RS-14. This tells astronomers something big. The galaxy's color doesn't always match its shape, especially in the early universe. And they're only just beginning to understand how galaxies grow and change over time thanks to this new technology. Thank you all for coming, and thank you to all my instructors. Please come check out my poster.
Good morning, everyone. Today I'll be presenting about the oxygen abundance in the Cecilia galaxy. Before I do that, I'm going to offer you guys some questions to reflect on it. So, when you look at the sky, what do you see? Maybe you see stars, sun, moon, clouds, but what else? And maybe some of you might know that we live in the Milky Way galaxy. But what any other galaxies are out there in our universe? And how old do you think our universe is now? I'm going to leave you guys that question while I explain about my research. So my research is about this ancient galaxy called Cecilia galaxy. It existed when the universe was only 2.3 billion years old, and for reference, the universe now is 13.8 billion years old. This plot here below is telling us the oxygen abundance versus the age of the universe. This line here shows us how oxygen abundance evolved chemically over time and age of the universe. So as you can see, when the universe is very young, starts at the age of 0 to 1, the growth of the oxygen is huge, and as the universe continues to age, it stays constant. The star here represents Cecilia Galaxy. It has the oxygen abundance of 8.05 oxygen to hydrogen ratio. So as you can see, this is lower than the average of the oxygen abundance in the universe. Why is that? If you want to learn more about it, you can check my poster. Thank you for all these of my instructors. They've been helping me, supporting me, guiding me throughout this entire program. I could not do it without them. Thank you.
Hi, everyone.
What's up?
Have you ever been a part of a team where you had a great idea, but you weren't sure if you should go for it or stick to the original plan? That same conflict is a classic problem in organizational science. My advisor, Professor Velez, she designed a brilliant yet highly complex and abstract experiment to test it. My challenge was to build a bridge between that complex theory and intuitive human experience. So I transformed that abstract theory into Exobal, a tactical fleet command game. Players now control a spaceship fleet facing the same exact mathematical trade-off as the original experiment, except now with an engaging context, which allows us to see how the participants improve, how their skills get better so that we can measure that. The result, it's a powerful new research tool that preserves 100% of the scientific validity of the original experiment while making the science more robust and human-centered. This work was only possible thanks to the immense support of the National Science Foundation's contribution to Princeton's Prison Teaching Initiative in the research experience for the undergraduate. That's a program I'm part of, okay? Okay, but all right, I'm going to go off script a little bit, okay? Beyond the data, okay? This project's success, it's a powerful prototype of a better way of doing things. It demonstrates that a non-traditional path, a unique lived experience, that it can be an asset to any organization. My journey from prison to the Princeton lab is a testament to this. The project's success validates the very programs that made it possible, like the National Science Foundation's contribution, okay? It's living proof of what happens when an organization takes a risk on human potential, demonstrating that the person who you become is always more powerful than the person you were. Thank you.
Good morning, everyone. Good morning. My name is Darius Murphy. I'm going to take you on a brief journey into the depths of time. Not through history books, but through galaxy. Galactic mergers are some of the most transformative events on Earth, in the universe. But unlike earthquakes, explosions here on Earth, we can't witness a merger in real time. Mergers take place over hundreds of millions of years, even billions of years. The article that started my research was an article called Memoirs of a Galaxy by Abby Lee. She summarized scholarly work from the University of Michigan, the Department of Astronomy, where they took AGB stars and RGB stars and did a ratio to see how old the stars were. From their graph, I wanted to see how old was our galaxy. So my hypothesis was we were in the younger range as some of the other stars here. So I did a few tests. My hypothesis come out to be incorrect because this graphs that I was able to come up with showed no correlation, which I end up paying attention to here. And when you see the range of error, if you actually see you actually understand the range of error, it showed that some of these plots here could have been over here or down here. So it actually showed no correlation. So my research brought that out. But what it did show me was that the evolution of the universe is similar to the evolution of what we find in this galaxy, which is it's a complicated one. It's a beautifully complicated one, but we have a lot more research to do to find out what it is. If you come see my poster, I can explain a little bit more. And switch the slide. I want to give thanks and acknowledgments to all of the instructors that helped us out. Thank you.
Good morning. My name is Patrick Pantusco. I am a Rutgers University student, and I am a Justice Studies degree candidate. I'm part of the ASAP, Aspiring Scholars and Professionals internship program here. I'm part of the PTI Presentation Initiative. And my internship practicum was about welcoming new employees to Princeton. I hope you all feel welcome here. And when I took on this job, it was my job to make sure that new employees felt the same way. My mentor, Mr. Nick Robinson, who is the executive director of the Campus Support Services, charged me with coming up with an onboarding document. And rather than just go with the traditional document, I created a website. My website introduces new employees to not only the job functions that they're responsible for, but it introduces them to their coworkers. And for everyone who keeps hearing that beeping, I apologize. I am still in a halfway house, and I need to keep my phone on. So what I did is I utilized AI to dive deep into the backgrounds of every employee who is currently working in Campus Support Services. It went through Indeed, it went through LinkedIn, Facebook, any articles that were out there, put together a narrative of this person's contributions to recognize and honor the contributions they've made to Princeton. And in my website, you can click on any employee from Campus Support Services and you will see everything about them. And you will see the areas that they work, their responsibilities. And it's a way to have new employees not only feel included in that, but to recognize the accomplishments of those they're working with. So if you want to learn more, come by. My website is fully operational. And I'd like to thank the Emma Bloomberg Center for access and opportunity, Princeton University, Dr. Ofori Mensah, who invited me into this program. And I listed quite a few people here, but most of all, I'd like to thank Mr. Nick Robinson for trusting me with this job and for having faith that I would complete it. Thank you, sir.
Hello, everybody. My name is Owen Pichardo, and today I'm thrilled to take you on a journey back in time, billions of years back, in fact, to explore the birth and growth of galaxies in our universe. The research that I conducted is important because it uses one of the most powerful tools we have in astronomy today, the James Webb Space Telescope, or the JWST. Think of the JWST as a supercharged pair of glasses that lets us see the universe in stunning detail, especially the very early galaxies that formed shortly after the Big Bang. Now, why does it matter? Well, understanding how galaxies formed and evolved help us understand the bigger picture of how the universe itself came to be. It's like trying to understand how a forest grows by studying the trees, except in this case, the trees are galaxies and the forest is the cosmos. I created a graph of basically, which is galaxy brightness against redshift. While you look at this chart on this slide, each of the dot that you see is represented by the average of galaxies. The dots that are higher show that those galaxies are younger, while the farther ones are older and dim. The line on the chart shows a trend that happens over time and that they help us see patterns in how galaxies have changed. One of the most fascinating things I learned is that galaxies that are younger in the universe are actually brighter. This also means that they were packed with stars and full of energy. Over billions of years, as the galaxies that are farther, these galaxies have dimmed. It's like a fire slowly burning out. This tells us that the early universe was a much more active place than it is today. JWST, the James Webb Space Telescope, allows us to measure these properties with incredible precision, up to 10 times better than older telescopes. That was a huge leap forward. It's like upgrading from a Polaroid camera to a high-definition one. With this clarity, we can now study the stellar masses of galaxies more accurately and understand how they grow over time. To get these results, scientists collected the data. I inputted the data to create scatter plots, added error bars to show uncertainty. I also used a polynomial curve to highlight trends. But you don't need to be a data expert to appreciate what this means. It's about uncovering the story of our universe, how it started, how it grew, and how it continues to evolve. In short, the research helps us piece together a cosmic puzzle. It is a reminder that even the tiniest dots on the chart can represent something massive and awe-inspiring. A galaxy filled with billions of stars, each of its own story. Next slide, please. I'd like to say special thanks to all you guys for joining and take this journey through space and time with me.
Since I was a kid, I have always been passionate about space and rocketry, with the dreams and hopes of becoming an astronaut one day. When we look up at the sky on a clear night with very little light pollution, we see stars and we envision distant galaxies. But what if some of those galaxies aren't like our own galaxy, which is the Milky Way? What if a single galaxy could help us determine the early universe better than thousands of others? Good morning, everyone. My name is Daniel Pipersberg, and I'm a rising junior transfer student at George Washington University. My research was focused on a distant galaxy which is classified as EXCELS 63107. This galaxy was formed approximately just 600 million years after the Big Bang. Using data from the James Webb Telescope, as well as illustrious simulated galaxies, I compared the chemical elements of carbon and oxygen abundance in this galaxy's gas and stars. Think of it like a recipe. If you know what ingredients you started with, which is the gas, and what came out of the oven, which is the stars, you can uncover the process that turned this raw material into something that's luminous. In both plots that you see on the screen, the x-axis shows the oxygen and carbon abundance in the galaxy's gas, and the y-axis shows how much oxygen and carbon is locked in its stars. But my galaxy, which is marked by the red and black stars, falls below the trend. My results show how we may be getting a rare glimpse into how the earliest galaxies in the universe evolved. Next slide, please. I would like to thank the following people who you see on their screen for their help and support this summer. As an aerospace engineering major and astrophysics minor,
This project really means a lot to me as it's giving us a window into early cosmic history. Because when we ask the what-if questions, we don't just explore galaxies, but we push the boundaries of our own potential. You can learn more about my research in the second poster session. Thank you, and God bless.
Good morning, everyone. My name is Naeem Santiago. I'm a student at Rutgers Camden. My title is called Pieces Coming Together. Galaxies seem mysterious, but we exist in a vastly beautified, spacious collection of materials that are more so unidentified to untrained eye and mind. Our galaxy, the Milky Way, is a collection of sun, moon, stars, and planets that provides us with amazing insights and enormous questions about life that we know and life that we don't know. My research is based on the Astrobites article titled Pieces Coming Together. Essentially, it proposes that all structures, galaxies, are built up of smaller pieces coming together to make a massive galaxy, a masterpiece like Legos. My question stemming from this research is how many major mergers existed or have taken place? Of course, there were too many to examine them all. I identified a specific data set, utilized Python coding to analyze, synthesize, reduce the data, and create a customized chart to provide insights and answer my question. On the x-axis, we have categories for ranges of time, 3 different spans, ranges on time scale. From 13.8 billion years ago, 4.7 billion years ago, and 7.9 billion years ago. On the wide hatches, we have the number of mergers, telling us how many mergers have taken place at those ranges of time. I believe that understanding the formation of the galaxies that we know can help us to understand the potential of what can happen through mergers. It is observed that our galaxy, the Milky Way, has a close neighbor called the Andromeda. It is believed that one day they're on track to merge. What this means for us, I do not know. But it's worth noting that galaxies consist of a process that is a collision that could be very violent. Yeah. If you'd like to know more about mergers, please visit my post. And I'd like to give special thanks to everybody. Special thanks to everybody that helped us, encouraged us, and pushed us along and helped us along all throughout the summer. I appreciate everybody. I can't thank you enough. Thank you.
Hey everyone, I hope you're all comfortable. My name is Hardwick Stiers, but it's going to be a lot easier, just call me Wicks. The last few weeks, I've been perusing the data on star formation rate and its relationship to metallicity at very distant galaxies. First, I'm going to elaborate on metallicity. As far as astronomers are concerned, anything heavier than helium or hydrogen, they're calling it a metal. And second, studying galaxies at extreme distances has been very difficult until very recently. Earth telescopes have always been very limited and couldn't really capture the data, and the Hubble telescope had very dated technology. But that changed with the James Webb Space Telescope. Because of its recent manufacture, it had been equipped with enough technological capability to capture data, as you can already tell, extremely distant galaxies. That said, astronomers have known for some time that galaxies, in the process of forming stars, tend to build up heavier elements or metals. As a general rule, it had been found that star formation and metallicity are highly correlated. So, to test whether this relationship stays consistent over cosmic time, I used galaxies from the illustrious TNG simulation. I grouped these galaxies by their distance from Earth and compared their star formation rates with their stellar and gas metallicities. I found their findings to be accurate, and their data from the simulation proved to be consistent. The shape between the 3 main comparisons remained consistent. Thank you. If you have any questions, come to my poster. Change the slide.
Hello, everybody. My name is David Ook, and my project explores how stress granules form. Imagine pouring olive oil and balsamic vinegar onto a plate. They don't mix right away, but if you stir through it, little droplets of vinegar will form in the oil. That's called space separation. Two parts of liquid that temporarily split into different sections. Inside our cells, the same thing happens under stress. When things get too hot or too unstable, certain proteins and RNAs will come together into droplets called stress granules. These act like emergency shelters, quickly pulling in together important molecules and protecting them while the cell rides through the storm. This kind of separation happens under certain conditions. On the left diagram right there is called the phase diagram. You can see the critical temperature and the density. Each curve shows a temperature range where phase separation is possible. If the conditions fall within the range, droplets form. If they're outside, the protein stays mixed. Right below it is a bar chart that shows the critical temperature for each protein, the specific points where they begin to form droplets. Each bar is color-coded by the net charge, which reflects how electrically positive and negative the protein is. You can think of the charge as like a personality. Proteins with a high charge might be more reactive or selective on people who they hang out. They might be more reactive or more selective, like people who only hang out with a certain type of people. A protein with high critical temperature can still form droplets even in warmer conditions, making it more stable or sticky to the behavior. On the right, you can see the simulations of 5 different proteins tested one by one. We wanted to know, can these proteins form droplets entirely on their own? For one of them, the answer was yes. It's built into dense droplets without needing any help. The others formed at lower temperatures that were really low in freezing. So not all the proteins to the stress granules form in the same way. Some of the independent builders, others are more specialized and need partners or precise conditions to do their part. By understanding their behavior, including how net charge and temperature affect them, we can get a clearer picture on how stress granules form and how they might go wrong. Thank you, and if you want to find out more, come by my poster.
Good morning, everybody. So, this summer, my research was tasked with dealing with Homer's Odyssey. So, Homer's Odyssey was originally written in Homeric Greek in around the 8th or 7th century BC. It's actually one of the oldest living pieces of literature still left around that's relevant in academic environments. So there's been about 60 translations of the Odyssey having been transcribed in English. I was tasked with taking 2 of those. Emily Wilson, who's the only female to have ever produced a translation, and Daniel Mendoza. So what I specifically was tasked with doing was putting those texts side by side and comparing them as it relates to tone, characterization, and diction, and seeing what each author was doing with those things to find out whether or not those things could provide a reader of both of those texts a similar story, right? Even though it's 2 different authors, and it did. So to give you a little insight about what tone, diction, and characterization is, tone is that the thing that basically it's the emotional quality or attitude in the language and establishes the overall mood and feel of something we're reading. Diction relates to an author's specific word choice, language, alignment of words, and characterization basically is how an author builds a character by attributing language and diction to that character. And oftentimes when we read books, we have this connection or lack thereof. Maybe we like a character, we love a character, we don't like the book at all. These all have to do with tone, characterization, and diction. And these things often go unnoticed, and us wondering why we have these connections, whether visceral or, again, negative outlooks on whatever we're reading. So what I did was I took a passage from each author's text and put it side by side. It's a little bit nuanced, my research, so I'll explain better if you come to my table. However, what I did was put them side by side Just take a passage and look how each used language, each used diction. And what's funny is you see that there's different word rhythms based on how long a passage is or how short it is. Emily Wilson's language was more modern, so it was easily identifiable and relatable for a modern reader. Daniel Mendelsohn, his text was more traditional and classical, and kind of like you got the sense that you were reading about nobility and reading about the time in which that text, which Homer wrote his text. So again, there's a lot to talk about. I attributed some music, lyrics and music define a song, right? It has tone, characterization, and diction. So what I did was I found 2 songs, picked one for each passage, and I'll explain that there. If you come and see me, and a little bit more about my research, I'd like to give some acknowledgments here. And thank you everybody for coming, and thank you guys for your performances. They were great.